I'm going to talk about considerably crazy possibility that the Lorentz invariance, the Lorentz symmetry of particle physics is an accidental symmetry, is an emergent symmetry of just the low energy approximation. Okay, so this is mostly based on this work, which after a long time finally appeared, plus some more work in progress. So that's overall in collaboration with Sergei Sibiriakov and two students, Grisha Betnik and Matteo Baggioli. So this Lorentz invariance has an accidental symmetry. So the pictorial metaphor for that is this kind of object, which of course, if you look at it from far enough, resembles a hyperboloid and realizes such a symmetry. But if you look from it, if you look at it from close enough, you realize this is not really the actual symmetry. In the much more concrete context that I will be having in mind will be the context of non-relativistic quantum gravity or Java gravity, where in the low energy perspective, this issue, the issue of how the hell does this theory recover Lorentz invariance at low energies, is the most pressing issue, without an exaggeration. Okay, and I'll try to convince you why. So just to start making things a bit more concrete, so for the sake of this talk, let's just think that we badly break Lorentz invariance by this sort of pattern. So we respect translations, space-time translations, and rotations. So this is the type of breaking that a vector, a space-time vector, condensing into a time-like direction realizes. Okay, a homogeneous vector. And this type of vector is the one that is in one way or another inside this Horjava theory, and okay, we can call it an ether. But the important point about this vector is that it has, of course, in this setup some dynamics and some scale at UV scale, from which, so at scales larger than this Lorentz violation, a scale so at energy larger than this, the theory looks completely not relativistic, okay, with anisotropic scaling and whatever you want. But at scales below this, the theory basically resembles GR plus some stuff, which is the fluctuations over this VEV, basically. And the only thing that I want to say in this talk about the gravitational aspect of this type of proposal is that it's basically, or it can be made basically healthy, in the sense that there are no pathological modes propagating, and it's relatively easy and reasonable to pass all observational tests, okay, by choosing reasonable parameters, not going to any corner in parameter space. And all the observational bounds that come directly from the gravitational sector are summarized into the fact that this scale of Lorentz violation has to be a bit below the Planck scale, a bit being 3 or 4 orders of magnitude. With this, you are done by passing observational bounds coming from gravity. Okay, so these bounds come, if you want to be more specific, from solar system tests, okay, on Lorentz violation. So then, since the topic, as you will see, is rather different than just the purely gravitational dynamics of these theories, I will leave it here. Let's just assume that there is this UV modification, which is really involves a really high energy scale, and let's now concentrate on the real issue, which is the matter sector. Okay, so the bounds, the observational bounds in the matter sector, okay, if we try to embed the standard model in one way or another in this type of setups, are very serious, okay, because by the same symmetries that we have, the same gauge symmetries of the standard model, we have at our disposal mu operators, which are in the form, most importantly, of the differences in the speed limits for different species, okay, different speed limits for the fermions, for each of them, a different speed of limit for the light for light and for the gauge bosons, and a different speed limit for the Higgs. Okay, so and this is only if there are of course even more operators if we do not restrict to be CPT even. Okay, if we allow to break CPT, then there are even more operators at dimension 3. Okay, but let's just restrict this, assume CPT just for simplicity. Okay, and now the issue is very simple. Once you allow this type of operators, these new types of parameters, the observational tests on them are very stringent. Okay, on the level of 10 to the minus 15 or 10 to the minus 20 for the electron or the proton, for instance. Okay, so these are very small numbers, and if we are reasoning in the with effective field theory logic, we would expect that these dimensionless numbers are of order 1 or a little loop suppressed, but not by not many orders of magnitude. Okay, so and this is what's known as this Lorentz fine-tuning problem.
Here the expectation is what here, right? In some
this
the Planck scale, there's
of a standard model with Lorentz violation. Okay, this is this type of EFT analysis, which we are simply
10 to the minus 3.
So yeah, this accounts because if you, I'm anticipating a little bit things here, because running by running at one loop, we will see that magically this delta C's can be loop suppressed. So this is what this 10 to the minus 3 is standing for the moment. But so even by including this type of arguments, you will see that you have a large discrepancy with what you really need to suppress at one loop. Okay, so I'm simply anticipating a little bit. Let's just keep it with order 1 at this level. So so just then to have simple ideas in mind, let's stick to this number 10 to the minus 20 as the goal that we want to beat. Okay, can we suppress this type of operators naturally by 20 orders of magnitude? Okay, if so, then we can claim that this Lorentz symmetry can be an emergent symmetry. Okay, so now once we are aware of the challenge, the good news come into the fact that there is a very well-known mechanism that almost does this job for us. Okay, and this is simply the RG flow. Okay, so it's known since 30 years now that the Lorentz invariance tends to appear as an emergent symmetry of the low energy of the infrared fixed points along the flow. Okay, so that was realized by Nielsen basically, and I'm trying to illustrate this simply here with the simplest example of a Yukawa theory with a boson and a fermion that I enlarge by including this delta C, different speed limits for the two species. Okay, so you can simply renormalize this theory. At one loop you have to include these new diagrams, and it's very simple it's very easy to work out what the running of these new couplings, these two delta C's, and you find that not surprisingly these delta C's run logarithmically with the RG scale, and this is basically if you expand where this 10 to minus 3 was coming from. Okay, so
this running will stop once you get to the weak scale or something, right? Once you get to some massive.
Of course, yes. So in the not so intuitive thing is that this logarithmic running of the delta C's is in such a way that it tends to shut down, to send the delta C's to 0 at low energies. Okay, and this is the good news. And however, the good news are not very exciting, because, by the way, this also happens in the standard model. This happens basically irrespective of the field content that you want to throw in this exercise. Okay, any field content that you can imagine in a weakly coupled theory will share this feature. The delta C's shut down to 0 at low energies. So then in the pictorial summary is like this. So this RG flow is, if you could make it very long, it would be a very slow flow to this nice place, Lorentz invariant place. Okay. The problem with this is that it's too slow, and if we run from this Lorentz violation scale, or close to M Planck, down to the electroweak scale, this is a factor 10. We are suppressing delta C by factor 10. Too bad. Okay. So we need to do better. But of course, there is a very simple modification of this idea, which is let's go wild, let's go strong, and let's accelerate this running. Okay. So yeah, very simple, but a bit hard to implement. So the idea in equations is basically this one. We have the same running of this delta C, and now if we are so lucky that we are sitting on a fixed point, then this is very simple to solve, and it simply exponentiates into a power law. Now a power law can be a much more efficient suppression of the delta C, and now the only thing that remains to clarify is whether the exponent, first of all, it can be positive. Okay, it has to be positive if we are to recover a Lorentz invariance in the infrared. And this is the second part of the good news. This exponent is granted to be positive. Okay, why? Because of unitarity. Because now we can try to see what we are doing here from the point of view of the infrared. What we are doing is we are adding perturbations to the Lorentz invariant theory of this form. Okay, a kinetic term with a little discrepancy in the time part with respect to the space part. Okay, but this is the time component of a spin 2 operator, of an operator with two indices. Okay, and in unitary theories, spin 2 operators obey a unitarity bound, which ensures you that the dimension of this operator has to be bigger than 4 in 4 dimensions. Okay, so therefore you are guaranteed that this delta C is a strictly irrelevant operator. Okay, strictly irrelevant because the only spin 2 operator which has dimension strictly 4 is the stress tensor, and doing the perturbation by the energy density, the time component of the stress tensor, wouldn't do anything. Just it's equivalent to a rescaling of time, as shown explicitly by Raman in a paper that I forgot to include in this slide. Okay, so so what does this argument tell us? It tells us quite a bit. It tells us that first of all, if we're letting the coupling go strong, any coupling of this let's say CFT be strong, then this exponent is going to be positive. Okay, because this is going to be an irrelevant operator, and if the coupling is stronger, this is more irrelevant typically. Okay, so the stronger the better. The stronger the coupling, the faster we go to the Lorentz invariant fixed point. Okay, which is this picture of the cascade. And the other thing that this suggests is that this phenomenon, the phenomenon of the emergence of Lorentz invariance, may not be that exceptional as it looks at first. Okay, let me clarify this this is not proving that this is going to happen always, by no means. Here, implicitly, I have been assuming that this low energy fixed point has isotropic scaling, is a z equals 1 fixed point. That by no means is a relativistic theory in the sense with a universal limiting speed. Okay, then what this argument is telling you is that if z equals 1 and CPT also, then the stronger you make the coupling, the faster you go to a universal Lorentz invariance in the infrared. Okay, so of course the job to do is to try and test this idea, and the handle to go through this strong coupling will be holography. So I'll discuss two toy models, if you want, to see what's happening and whether we can confirm this. So the first is in a Lorentz violating version of this Randall syndrome models, okay, which is the usual, okay, a slice of ADS. Modes confined in the interior are interpreted as composite states of the CFT. Modes localized close to the UV are interpreted as elementary states. Okay, and in this logic, it's very simple to realize holographically. For instance, a simple model like this, where I'm considering a CFT that has in its spectrum a scalar operator of dimension delta, and particle, if you want, of dimension delta, which, if I set this coupling lambda to 0, is simply decoupled from another sector, which is an, let's say, elementary sector, which I call phi, which is non-relativistic. Okay, so now I'm using conventions where the emergent speed, limiting speed of the CFT is normalized to 1. And the one of this non-relativistic sector is C. Okay, it could be a function of K if you want. And now the one check that we can do is let these two sectors interact with this lambda and see what happens. What should happen is that it depends on the nature of this coupling. If this coupling is relevant, then the interaction between these two sectors wants to grow in the infrared, and you should expect the Lorentz invariance to really emerge, or in this type of model to persist in the infrared. Okay, and if this coupling lambda is irrelevant, you shouldn't get this emergence. And this is exactly what happens. Okay, so the first simple argument is okay. Let me simply integrate out this CFT, okay, including this O, and you can work out this effective propagator for the phi field, the elementary field. You have a CFT self-energy correction that scales with this exponent, and this exponent dominates in the IR. So this P square is the Lorentz invariant combination of omega square minus k square. So with C equals 1 here. And so this is a contribution that is Lorentz invariant and dominates the infrared, provided this delta is less than 3, okay, which is exactly the same criterion that this coupling is relevant. Okay, so you can do, of course, a bit more sophisticated tests, and by letting this model have an infrared confining brane, you can work out the spectrum of the bound states, the dispersion relation of the Kaluza-Klein modes, which are the bound states, the resonances of this theory, and you can work out with all details these dispersion relations, and the leading Lorentz violating correction is in the form of delta C, a different speed limit, that interestingly scales with the confinement scale, the confinement scale that the infrared brane defines for you. Okay, and it scales exactly by this exponent, which is dictated by this the dimension of this scalar operator. Okay, so now the interesting thing is that this is power law suppressed, and therefore, provided this power is order 1 and this ratio of scales is big enough, this correction, this Lorentz violating correction, can be really small. Okay, so this is. I'm also including here the higher order corrections to this dispersion relation, but they are not big in any regime. So let's forget. So in this picture, I'm also including what happens with these dispersion relations of these Kaluza-Klein states in the case where it doesn't work. Okay, when the coupling is not relevant, it's irrelevant. And you see that really, since these are not exact hyperboloids, but some sort of interpolation between the usual hyperboloids of the would-be Lorentz invariant CFT and this non-relativistic external sector, since but in the generic case, so this is not obviously Lorentz invariant, so that's what you should get for the relevant case, okay? But for the relevant coupling, it works. So very good. So
sorry, in that formula, so the lambda is the coupling to the Lorentz violation sector. Then why lambda going to the downstairs?
Yeah, because this lambda is so in a way you can interpret that this lambda together with these factors that are energy dependent. Okay, the relevant scale here is this composite inertia scale. So this is in a way the running coupling, exponentiated. Okay.
Your lambda is defined as lambda UV.
Yeah. Lambda is the value of lambda at the UV scale.
Right.
Yeah.
But then if I make that lambda smaller, then somehow the effect is bigger.
Of course, that's what has to be. That has to happen because in the case where lambda is 0, what you have is a Lorentz invariant sector decoupled from a Lorentz non-invariant sector. The theory is by no means Lorentz invariant. Okay, it's not universally. Not all modes share the same speed. Okay, you have this light mode which has a small cone, and more light modes which have a different cone. The theory is not Lorentz invariant. So this only happens if the coupling is non-zero.
Sorry, this is the dispersion relation of what states?
So if the moment you turn on this lambda and you let the confinement scale to be small compared to the UV scale, you only get, what I'm saying is that you only get almost exactly hyperboloidal dispersion relations. So these modes fuse into almost exact hyperboloids, and the deviation from this is so small that you cannot tell. Okay, that's the point.
Is a normalizable coupling in the ultraviolet. So how can it appear in the denominator and the infrared?
So this is the value at the UV. Okay. That's what comes out of the computation, which you can do with all details in the holographic in the bulk. Okay. So, but it has this nice interpretation that.
So if you go to the previous slide.
Yeah.
So this is the green function of O, right?
This, yes. Yeah.
Yeah. So, but then when lambda equal to 0. Then you should see nothing of this phi at all. You will just see Lorentz invariant.
Right. So here, this is the green function of phi. This is the phi correlator. Okay, so you are only left with this.
You're looking at the green function of phi.
Yeah. So here the only technically important thing is that there are these two different powers of frequency and k dependent terms, and this can dominate the infrared, provided lambda is non-zero. Okay.
But if delta is equal to 2, then there's no contribution.
Right. Delta equals to 2 is a case a little subtle, and then you'll get logarithmic corrections. It's not easy to you cannot infer from this formula.
Okay.
Yeah. No, good point. Yeah. But the basic physics is this.
But you can systematically derive those logarithmic corrections?
Yeah. So then you can you can also consider a little bit more sophisticated models in the form of which are interpreted as RG flows between a Lifshitz scale invariant field theory and a Lorentz invariant field theory in the infrared. So these are well known by now, and the simplest model you can think of consists in the bulk of Einstein-Hilbert plus a massive vector field, okay, Proc theory. In this theory, with nothing else, there are these Lifshitz solutions. So you have you can realize a bunch of values of Z depending on the value of the mass of this gauge field. And interestingly, for one fixed value of the mass, you can have more than one value of Z. Okay, so and even more interestingly, there are solutions with Z bigger than 1 that can be connected to the solution with Z equals to 1, which is ADS. Okay, and so the flow that goes from this to here is an RG flow that exhibits Lorentz invariance of the universal sort that I'm discussing in the infrared. Okay, so this is the type of domain wall solutions that materialize these flows. And on these flows, you can do the same analysis. Okay, both on correlators. Okay, of course, since the infrared is anti-de-Sitter, the correlator is dominated by a Lorentz invariant part. This is the Lorentz invariant combination. And then there are Lorentz violating corrections, which are suppressed, okay, by a UV scale, okay, the scale of the domain wall, and which you can compute. And they are characterized now not only by the exponent associated by the dimension of the scalar field, which is what I'm taking here. This is a probe scalar field of dimension delta. So it's not only dominated by this delta, but also by delta 1, which is the dimension of the spin 1 operator that that dominates the flow. Okay, that gives the Lifshitz solution, the domain wall solution. So very similar thing where things were discussed by Gupser also in 2008. Okay, but with not Lifshitz UV region. So of course you can also analyze the dispersion relations of the bound states, and similarly you realize that this delta C is also a scale like a power law, but now the power law is dictated by this dimension of the spin 1 or of the spin 0 operator, depending which is the most the lowest power. Okay, so the lowest power of these two will be dominated. So this in this simple example that I'm discussing, this basically what dominates this Lorentz violating deviations is the dimension of the spin 1 operator, okay, which is not a very irrelevant operator, but so there is we're collecting evidence that by not so crazy changes in the model, this exponent can be made bigger, and therefore the emergence of Lorentz invariance can be made faster and therefore more efficient. Okay, so these small modifications of this model involve, for example, introducing non-minimal couplings of this vector to the metric. Okay, and this seems to do the job. You can increase this the dimension and make that the power in this suppression is easily of order 2. Okay, which is good. So I'm almost done. So let me just conclude by saying that if you just take the RG flow and you fuel it by enough strong coupling, indeed Lorentz invariance seems to emerge, and fast. Okay, fast, maybe fast enough for particle phenomenology, which I'm going to discuss. So okay, this maybe not such an exceptional phenomenon, and in a very one sentence summary, all the Lorentz violating corrections are dominated by this interesting notion, this LILVO, the least irrelevant Lorentz violating operator, okay, which is in any theory there will be one, and so it depends now on the model how large, so the larger this dimension is, the better, okay, for the matter of emergence. But okay, now it's a model-dependent question. So, so regarding,
Out of time, yeah.
I'm out of time, so I have almost nothing to say about condensed matter, so let me not say anything. And about particle physics, so here just the model-independent conclusion is that provided you have compositeness at a relatively low energy, which is now of order 100 TeV, you could arguably think that the Lorentz invariance can be emergent in this sense, okay? And this 100 TeV comes out by requiring that you have basically 10 orders of magnitude below this Lorentz violation scale, which I said before was 10 to the 15 GeV, basically. So, okay, and with this, if you are very optimistic, you can think that these non-relativistic quantum gravity theories, by insisting on naturalness regarding this Lorentz fine-tuning, so requiring absence of Lorentz fine-tuning, then these quantum gravity models become very predictive because they require new physics at a very low scale. Okay, and with that I'm done. Thanks.
The bottom line is, this unparticle physics, it's easy to generate Lorentz invariance at low energy. It's all about the particle physics. Guess there's time for a question. Brian in the back.
Yeah, so you talked a lot about velocities. What about if I did something like give electron and positron different masses?
Good. Yeah, this is a CPT odd operator.
Okay, but whatever. Suppose the CPT is broken.
No, if CPT is broken, this is not working. So that's what I meant by saying that I'm not claiming that this is a proof that this is always happening, but there are assumptions under which this thing happens. Assumptions are CPT even, so not breaking CPT, and assuming that the infrared goes to Z equals to 1. If so, the stronger the coupling, the better.
Mm-hmm.
Okay?
And are Goldstone modes dangerous since they decouple?
Goldstone modes, no. So well, it depends what you have in mind. So here it's not trivial regarding the embedding of the standard model in this picture. The gauge bosons are a concern. Okay, because the gauge bosons, localized or emergent gauge bosons, are a bit tricky. It's not completely impossible from my point of view, but Goldstones are not a problem here. So these resonances that I basically included in this picture could include some Goldstones. No problem with that.
Okay, I'm watching the clock, right? We need to find a time. Let's